So in this optimization specific question, we're going to analyze the area of a rectangle inscribed in a fixed right angle triangle. So here we have a rectangle which is inscribed. So as you can see, the four vertices of the four corners, D, F, and G, and C, the corners of the rectangle are making contact with the sides of the right angle triangle. So as you can see here, and the triangle is fixed, meaning the base is 8 and the height of the triangle is 4. So what I'm doing right now is moving the rectangle, so the area of the blue is being calculated right now, and we want to find the largest space or largest area rectangle, and let's just see what happens. Let's just say I make the width wider and the height smaller. What happens? The area is like 4-ish and it becomes really small, the area. But then if I go the other way around, meaning I want the height to be more, getting more taller, what happens? Oh, the area is 7.7, 7.8, 7.9, and somehow it's around, I believe the maximum area based on GeoGebra is around 8-ish, 7.99, and after, somewhere around here. But what happens after that? Once I move it, it becomes a little bit smaller. So we have already reached our maximum point here. So let's actually start to calculate this algebra-wise. Let's try to figure out the equation, the function to optimize. So we're optimizing the area of a rectangle. So once we know the type of measurement we're optimizing, that should start off with the function. Well, starting to get the function. So the area of a rectangle is length times width. I'm going to be using x and y. I'll let x be the length and y be the width. And because I'm using x and y, I'm going to have to label what is x and y in my picture. So I'm going to let this be x, and I'm going to let this be y. And so now we have a choice. Do you want a to be expressed on x or a expressed in terms of y? All right. So that's the question right now. But we need to find a constraint equation. So there's got to be something in this rectangle that's connected to the features of the triangle. All right, so let's have a look. So if you look at the rest of the triangle and connecting it to the rectangle, I'm just going to label everything that I know. So I know that from here to here is going to be, I don't want to call it another variable because I know the whole thing is worth 8. So that means if this thing is worth 8, that means this piece is 8 minus x versus this piece here. Up here, I know the whole thing is worth 4. So I'll put here 4. But this piece here, I don't want to use another variable, but I'm going to use y to help me get the other piece, which is 4 minus y. And if you had done the investigation, you would realize that there's something going on with the triangles. Now, in this shape here, we just don't have one big triangle, ABC, but we have small triangles. So as you can see here, we got a BDF, and we have DA, I think that's a G. So we have similar triangles. So when we have similar triangles, and well, why are they similar? So going back to grade 10, when you actually prove something we're similar. So the reason why they're similar is because I'm going to put here a little theta. These two angles are the same because of the F pattern, or I think you call it corresponding angles. There's another common angle because we know that these are all 90 degrees because they're parallel. These D and F and A and C are parallel, so we have another corresponding angle. And also, if you really wanted to, we can actually look at this other angle here. These two are also the same. Why? Because corresponding. I'll use red because here these two sides are parallel, and another corresponding angle. So we can say that triangle ABC, the big one, I'll put here the big triangle, is similar to triangle DBF. So over here, just to show you, DBF, which is also similar to ADG. So similar to ADG. So what that means is the sides, the ratios of the sides are going to be similar. So if I were to look at the height and the base, so the height here from here to here is AC. So AC over the base, which is BC, is going to have the same ratio as DF. So DF is over here. I'll use blue here. So DF over BF. So BF which is very similar to the medium-sized triangle up here, which is AG over DG. And then we just have to sub in the numbers that we know, or the values that we know. Another case, AC is going to be, AC is, whole thing is 4 over 8. DF, we called, so DF here, what did we call this? Oh, we call this Y. It's going to be Y over, in this case, 8 minus X, which equals to AG, so I'll use green color. So AG is over here, which is 4 minus Y, so 4 minus Y over, what's this piece here called? The base of the medium-sized triangle in my diagram. That's going to be, oh, we called it X. So now we have a ratio between X and Y. These are the constraints. So what that means is the ratio from the base to the height is always 4 to 8. 1 to 2 ratio, in other words. You can actually reduce this. Also, I'll reduce it from here to here, which is the same thing as 1 over 2. So to make my constraint equation, I'm going to take these two here, and write down the following. I'll put here constraint equation, that 1 over 2, the ratios, they have to be the same. Miss, do I have to choose the first two fractions or ratios? No, you can actually choose the first and the third if you wanted to. Would you choose from here to here? If you choose the second and third, it gets more complicated. You could, but I'm going to avoid having too much x and y's in my numerator denominator. So going back up here, this is my constraint. I'm just going to clean this up. That becomes 2y is equals to 8 minus x. And between, if you're to isolate one of these variables, which one would be the easier one to, I want to say easier, which one would you sort of avoid fractions if you want to avoid fractions? Well, I would isolate the x. I'm just going to bring the x to the left and then bring the 2y over, and this is my constraint. So now that's our constraint. Let's go back to the function. Don't forget, we have to go back to the function. So do you want to express a in terms of x or a in terms of y? Well, because I'm going to replace all the x's, I'm going to express everything in terms of y. In other words, a of y is equals to, okay, well, I'm going to put here x and y. And I want to keep the y, but I don't want the x. So what's x? So I want to express the function not in terms of two variables, but in terms of one, in this case y. I want to maintain the y, but this x has got to be sort of reformatted, replaced. Oh, here we go. X is the same thing as 8 minus 2y. And then we are done. In terms of having the function, Miss, can I expand? Of course you can expand. This is an easy one to expand because this is actually a simple quadratic function as a parabola that's facing down. And then next thing, we need to find the restrictions. What are the constraints? So what are the restrictions for y? So I'm going to go back here. Over here, I'll do it in dark here. What's the lowest that the y can be without using algebra? Well, the lowest the y can be is 0. All right. What's the highest that the y can be? Well, the highest the y can be is the height of the triangle. In other words, just based on looking at the picture, we can see that the height, the minimum is 0, and the maximum is 4. Now, it cannot equal to 4, it cannot equal to 0, because if it did, then you wouldn't have a rectangle that existed. And you can actually test it out by using the GeoGebra and actually moving the rectangle up and down, left and right. So we erase this part here. Now, if you're not comfortable getting the restrictions from a graph, you can do it algebraically like we did before. So how do we do that? So let's find the restrictions. So I'll use blue. We know that the area must always be greater than 0. So that means 8y minus 2y squared is going to be greater than 0. And we have another inequality again. But this inequality is a bit easier than the other ones that we dealt with because it's already in factored form. Well, we just factor it. And then we find the zeros. The zeros are 0. And we set this to equal to 0, which gives me y is equals to 4. Then we do our interval chart. And we set our, I'll put here y and then 8 minus 2y. And we put 0 and 4. I'll use a darker color. And then I know that for here, this is going to be you do all your signs. And ideally, I want everything to be positive. So if I put, for example, negative, positive, that'll be a negative, which I don't want. If I put, for example, 1, I get a positive and a positive, positive, which I do want, yes. But I choose a number that's bigger than 4, like 5, I get a positive and a negative, negative, which I don't want. So I know my restrictions are between 0 and 4. So I'm just going to finish this question off really quickly. So just wrote the function again, and then I just took the derivative using the power rule, and then I set it to equal to 0. I don't have a denominator, so I don't have to deal with the undefined derivative. I get y is equals to 2. Then I'm just going to show you the second derivative test. So second derivative test, So I'm not going to do the first derivative test. Remember the table that we always do to check whether it's positive or negative, whether the slope is positive or negative. I'm not going to do that. I'll do the second derivative test just to get some variety. What's a prime? Double prime. A double prime is going to be the derivative of this piece, which is just a -4. So what that means is no matter what happens, if I subbed in, for example, if I subbed in my 2 into here, I would always get a -4. What does that mean? Well, that means that the curve at 2 is going to be concave down. But here, CD, curving down at 2. And because the slope is 0 here, I know that this is a maximum. And also I know it's a parabola. And I know a parabola that's facing down has an absolute maximum automatically. And the last thing you have to do is check your endpoints, or your end behaviors, I'll call it. So meaning you're going to have to sub in 2 into your function to see what the area is. You get some sort of number. Then you have to look at the extreme cases. So remember our derivative, our restrictions was between 0 and 4. So then you got to test the end behaviors of the function. So put here y approaches 0 from the right. You're going to get a 0 because I know over here, and you're going to sub in. So you're going to figure out the limit of a of y as you come from the left. And then you're also going to get a 0. How do we get this 0? You just have to sub in 0 into the function. Also, if you want to see the actual function, you can type this function into Desmos and see the actual parabola. And you can actually find the max right away to verify your algebra.